A single solar flare can end a human life in deep space within minutes. This is the hidden reality of our cosmic ambitions. We are on the cusp of becoming an interplanetary species, yet every journey beyond our blue world is a high-stakes gamble against a universe filled with silent, invisible threats. Today, we will map the 25 cosmic hazards that stand between humanity and the stars, from the slow erosion of bone to the sudden fury of galactic explosions. By the end, you will understand the intricate web of dangers we must solve to ensure our survival out there. How does radiation we cannot see rewrite our very DNA over years? What happens to the human mind when Earth is just a distant, fading star? The answers define our future. What does it truly take for life from Earth to endure in the void? The most dangerous threat in deep space is one you can neither see nor feel. Galactic cosmic radiation is a permanent, high-energy storm that fills the void between stars, a relentless drizzle of atomic shrapnel born from the explosive deaths of ancient suns. Imagine standing in a quiet meadow during a gentle rain, but each raindrop is a proton or the nucleus of an iron atom, moving at nearly the speed of light. On Earth, our planet's magnetic field and thick atmosphere act as an umbrella, deflecting and absorbing this downpour. But in interplanetary space, that umbrella is gone. An astronaut on a journey to Mars would be exposed to this radiation for years, with only the thin skin of their spacecraft and their spacesuit for protection. It is a silent, invisible siege against the human body. The danger lies not in a single, catastrophic dose, but in the cumulative, insidious damage. These high-energy particles are like microscopic bullets. They can pass straight through the hull of a ship, through an astronaut's body, and through the very heart of their cells, directly striking and breaking strands of DNA. The body's repair mechanisms can fix some of this damage, but over months and years, the errors accumulate. This significantly elevates the lifetime risk of developing certain illnesses. Research also suggests prolonged exposure could affect the central nervous system, potentially impacting cognitive function and memory, which are critical for mission success far from home. Perhaps the most daunting challenge is that shielding against this type of radiation is extraordinarily difficult. Unlike the radiation from a solar flare, which is mostly lower energy protons that can be blocked by a storm shelter with thick walls, galactic cosmic rays are so energetic they can cause a cascade. When one of these heavy, high-speed nuclei strikes the atoms in a spacecraft's aluminum hull, it can shatter them, creating a secondary shower of even more particles inside the living quarters. In some ways, a simple metal hull can make the problem worse. So how do we protect our explorers? Engineers and scientists are pursuing multiple, layered solutions. One visionary concept involves creating an artificial magnetosphere around the spacecraft, a miniature version of Earth's protective magnetic bubble to deflect the charged particles before they hit the hull. Other designs use passive shielding, like positioning the ship's water supply or even the crew's waste in strategic walls around the habitation module, as water is excellent at absorbing this radiation. There is also active research into pharmaceutical countermeasures, compounds that could be taken by astronauts to help their cells better repair radiation damage or flush out harmful byproducts. The fundamental question we must answer before any multi-year mission is this: what is an acceptable level of risk for a human life spent under this unseen storm? Defining that limit will shape every aspect of the spacecraft we build. While galactic cosmic radiation is a constant, silent siege, the sun delivers its fury in sudden, violent outbursts. A solar particle event is the star's tantrum, a cataclysmic explosion that can change everything in an instant, During these events, the sun's tangled magnetic fields snap, violently ejecting billions of tons of superheated plasma and charged particles across the solar system. This storm travels at a significant fraction of the speed of light, meaning a warning from solar observatories might give a crew only tens of minutes to find shelter. For astronauts in interplanetary space or on the surface of a world like Mars, which lacks a global magnetic field, there is no natural protection. The radiation from a major event is intense and immediate. Unlike the slow accumulation of galactic cosmic rays, this is an acute, overwhelming dose. Exposure could lead to severe health consequences in a very short time, potentially affecting the central nervous system and other critical bodily functions. The danger is not theoretical. History offers a sobering near miss. In August of 1972, between the Apollo 16 and 17 missions, one of the most powerful solar storms ever recorded erupted. Had astronauts been walking on the lunar surface at that moment, outside the relative safety of their lander, they would have received a life-threatening dose. That event serves as a permanent reminder of our vulnerability to our own star's unpredictable moods. Our primary defense today is the storm shelter, a heavily shielded compartment within the spacecraft or habitat, often lined with water, food, or polyethylene to absorb the incoming particles. But this solution presents its own harsh realities. A shelter must be small to be effectively shielded, meaning a crew could be confined to a cramped, windowless space for hours or even days, waiting for the storm to pass. And what if the warning comes too late? An astronaut caught on a surface excursion too far from their rover or base to return in time faces an impossible scenario. This unpredictability weaves a thread of psychological stress throughout every mission plan. Crews must live with the knowledge that their life-giving star could, without much notice, become a lethal adversary. It transforms mission planning into a high-stakes gamble with solar weather, where a single forecast error or a surprise eruption could rewrite the entire story. This leads us to a third, more pervasive threat, one that works in concert with both forms of radiation to weaken the human body from the inside out. The floating body is being quietly dismantled from within. In the perpetual freefall of microgravity, the human form receives a cascade of deceptive signals, convincing it that the hard work of supporting itself is no longer necessary. This is not a sudden failure but a slow, systemic unraveling. Without the constant pull of Earth's gravity, bones begin to shed their mineral density at an alarming rate, as much as 1 to 2% every single month. A 6-month journey to Mars could see an astronaut's skeleton age the equivalent of a decade. Muscles, especially in the legs and back, atrophy from disuse, wasting away without the daily resistance of simply standing and walking. The body, in its ruthless efficiency, reallocates energy away from what it perceives as unnecessary systems. But the strangest effects are perhaps the most insidious. Bodily fluids no longer pull downward, shift toward the head. This fluid redistribution can cause chronic sinus congestion, a puffy face, and more worryingly, increased pressure inside the skull. For some astronauts, this has led to lasting changes in vision, a physical reminder of the environment's profound impact. The cardiovascular system grows lazy and weak, struggling to maintain blood pressure upon return to gravity. Even the immune system shows signs of confusion, reacting differently to challenges than it would on Earth. To fight this slow-motion decay, life on the International Space Station revolves around a brutal, non-negotiable routine. At least 2 hours of intense daily exercise, strapped into specialized machines that simulate weightlifting and running. It is a daily battle against atrophy. Yet for a multi-year mission to Mars, this regimen presents a monumental challenge. The exercise equipment itself would add critical mass and power requirements to the spacecraft. More fundamentally, even with rigorous countermeasures, some level of physical degradation seems inevitable. The haunting question for mission planners is not just whether astronauts can survive the journey, but whether they could possibly arrive on Mars in a condition to perform complex, physically demanding tasks, like constructing a habitat or exploring rugged terrain, after months of their bodies being conditioned for floating. This hazard forces us to confront a biological truth. We are not simply visitors in space, we are intruders. Our entire physiology is a product of Earth, fine-tuned over millions of years for its specific gravitational pull. To leave is to enter a state of profound physiological conflict, where survival requires fighting our own body's adaptive instincts every single day. And if the environment itself is working against human biology, what unseen threats might be lurking within the confined world we build to survive it? The spacecraft's hull can be reinforced, but the human mind remains the most fragile system on board. Inside a habitat no larger than a modest apartment, a crew of 4 or 6 will live, work, and breathe together for over 2 years, with Earth reduced to a pale blue dot, and then to nothing more than a bright star in a black sky. This is the ultimate test of isolation and confinement. The dangers here are not meteors or radiation, but the slow, creeping pressures of an existence stripped of all familiar anchors. Research from extreme environments on Earth, like winter over cruise in Antarctica, shows a predictable pattern. Initial excitement gives way to monotony, then to irritability and social friction. In a place with no new scenery, no fresh faces, and no escape, minor annoyances can magnify into deep-seated conflicts. Cognitive fatigue sets in, dulling decision-making at the very moments it may be most critical. The mission's success hinges on flawless teamwork, yet the environment itself works to erode the bonds that make that teamwork possible. Perhaps the most profound psychological challenge is what some call the Earth out-of-view phenomenon. For the entirety of human history, our home world has been the constant background of our existence, physically beneath our feet or visually present through a window. On a journey to Mars, there will come a point where Earth shrinks to just another point of light, indistinguishable from the countless other stars. This can trigger a deep, existential loneliness, a visceral understanding of just how far from home one truly is. The comforting psychological connection to humanity, to family, to green hills and blue oceans is severed. To combat this, mission architects are designing digital lifelines. Virtual reality could offer immersive escapes to a forest or a beach, a necessary reset for the senses. Artificial intelligence companions are always available for conversation or to monitor a crew member's speech patterns for signs of distress, could provide a form of social support. The crew selection process itself becomes a science of predicting compatibility under unimaginable stress, seeking individuals with not just technical skill, but extraordinary emotional resilience and conflict resolution abilities. Their daily routine will be meticulously structured, every hour filled with purpose, because idle time in such confinement is a dangerous vacuum. This hazard asks a fundamental question about our nature. Are we, as a species, built for such profound separation from our world? The integrity of the mission depends on the answer, proving that the final frontier is not just a physical space, but an immense psychological wilderness. And within that confined metal world, another invisible threat is already growing, born from the very systems meant to keep the crew alive. Stepping onto an alien world is not an arrival, but a transition into a new and hostile ecology. The thin, rust-colored plains of Mars may look serene from orbit, but they hold a trifecta of silent dangers. First is the dust, a global, fine powder as abrasive as ground glass. It does not settle like Earth dust. It clings, infiltrating every seam and joint. Inhaling this material, which contains perchlorate chemicals toxic to human biology, could pose serious long-term health risks. turning every surface excursion into a delicate dance of contamination control. Then come the temperature swings, a brutal cycle where a summer day at the equator might feel almost pleasant, only to plunge to depths far colder than Antarctica at night, stressing materials and suits to their limits. And above it all, the thin Martian atmosphere is a false promise, too sparse to breathe yet thick enough to kick up global dust storms, while offering no meaningful shield against the relentless radiation from above or the occasional micrometeoroid impact from below. Every habitat, every rover, every spacesuit must be engineered as a fortress against this triple assault. The Moon presents a different, yet equally sinister, challenge. Lunar dust, called Regolith, is not merely dirt. It is the shattered remains of ancient impacts, a powder filled with microscopic, glass-like shards. Because there is no air or moisture to soften its edges, it remains sharp and abrasive. In the airless environment, it becomes electrostatically charged by the solar wind, levitating and clinging to everything: visors, spacesuit fabrics, and especially machinery. During the Apollo missions, this dust quickly clogged tool joints, abraded helmet visors, and even caused temporary breathing issues for astronauts when tracked back into the lander. For a long-term lunar base, this omnipresent grime threatens to jam airlock seals, short-circuit electronics, and potentially damage lung tissue if not meticulously managed. It turns routine maintenance into a constant, gritty battle. These challenges, however, pale in comparison to the ultimate planetary gauntlet, the surface of Venus. Here, the environment is less a puzzle and more an act of outright violence. The pressure is 90 times that of Earth's, equivalent to being nearly a kilometer deep in an ocean. The temperature is hot enough to melt lead, and the thick, yellow clouds rain sulfuric acid, sending humans with current technology an impossibility. Surviving would require not just a habitat, but a veritable submarine designed to withstand crushing forces and corrosive chemistry, a stark reminder that not all worlds are welcoming. Each new destination demands a bespoke survival strategy. A Mars habitat may need advanced filtration systems and double-door airlocks designed as dust traps. A lunar base might require an entire module just for decontamination, using electrostatic curtains or even liquid baths to clean suits before re-entry. These are not mere engineering details, they are the fundamental parameters of life off-world. This forces a profound realization: in space there is no benign environment. Every step onto another celestial body is a step into a new and intricate web of threats, where survival depends on anticipating the unique hostility of each new shore. And if the very ground beneath our feet is adversarial, what unseen biological dangers might we carry with us or find waiting? The silence of space is broken by a violent, microscopic impact. Traveling at incomprehensible speeds exceeding 20,000 miles per hour, even a fleck of paint or a grain of sand becomes a hypervelocity projectile. These are micrometeoroids, natural fragments from asteroid collisions or the dusty trails of comets, and their human-made cousins, orbital debris, which together create an invisible shotgun blast spread across the solar system. At those velocities, kinetic energy transforms the mundane into the catastrophic. A particle the size of a pea could strike with the force of a bowling ball dropped from a skyscraper, while something as small as a paint chip carries the punch of a high-caliber rifle round. For a spacecraft's thin hull or the delicate layers of a spacesuit, a direct hit from even a tiny object is not a dent, it is a catastrophic puncture. A breach in the pressurized living quarters of a ship millions of miles from home is a scenario mission planners train for relentlessly, a race against the clock to locate and seal a tiny, whistling hole before the atmosphere escapes entirely. The danger is compounded in the space around our own planet. Decades of launches, explosions, and collisions have littered Earth's orbital highways with a cloud of debris, from defunct satellites to discarded rocket stages and countless fragments. This introduces a frightening possibility known as the Kessler syndrome, a theoretical cascade where one collision creates hundreds of new pieces of debris, each capable of causing another collision, eventually creating a self-sustaining shell of shrapnel that could render entire orbital regions impassable for generations. It is a potential trap of our own making, threatening to imprison future missions before they even leave our neighborhood. So how do we armor our vessels against this relentless, high-speed rain? The most common solution is ingenious in its simplicity: the Whipple shield. Named for its inventor, this is not a single thick plate of metal, but a layered defense. The outer bumper shield, often a thin sheet of aluminum, is designed to be sacrificed. When a projectile strikes it, the impact vaporizes both the debris and a portion of the shield itself, transforming the solid bullet into an expanding cloud of gas and molten droplets. This cloud then spreads out, distributing its remaining energy over a much wider area of the much stronger inner hull, which can safely absorb the blow. It is a concept of taking a pinpoint spear thrust and turning it into a gentle, manageable push. Research continues into even more advanced materials, like self-healing polymers that can automatically seal a small puncture, or metamaterials designed to dissipate impact energy in novel ways. Yet for a years-long interplanetary cruise, no shield can be 100% perfect. Engineers must grapple with statistics and probabilities. The longer the mission, the greater the cumulative chance of encountering a particle large enough to defeat their defenses. Hull integrity thus becomes a non-negotiable, ever-present whisper in the background of every deep space journey, a reminder that the void is not empty but filled with silent, high-speed bullets. This constant physical threat exists alongside a more subtle, internal danger, one that can compromise a mission from within without a single impact. The final frontier is a place of profound silence, not just of sound but of connection. As a spacecraft ventures farther from Earth, the speed of light itself becomes an adversary. Radio signals, our only tether, travel fast but not instantaneously. At the distance of Mars, this creates a one-way communication delay that can stretch beyond 20 minutes. A simple question from an astronaut to mission control takes over 20 minutes to arrive, and the answer takes another 20 minutes to return. In a crisis, that 40-minute lag is an eternity. This transforms the relationship between crew and ground support entirely. Mission control shifts from being a real-time partner to a distant, delayed advisor. For the first time in the history of human exploration, a crew facing an emergency, a sudden hull breach, a critical system failure, a medical issue, must diagnose the problem, weigh their options, and execute a solution completely on their own, with no one to call for immediate guidance. Their training must prepare them not just to follow procedures, but to write them in the moment under immense pressure. This operational isolation is punctuated by total communication blackouts. During solar conjunction, when Mars moves directly behind the Sun from Earth's perspective, our star's furious radio noise drowns out all signals for weeks. For that period, the crew is utterly alone, cut off from any new data, advice, or even simple messages from home. The psychological weight of this silence is immense. The comforting chatter of mission control, the daily news updates, the personal video calls with family, all of it vanishes. The crew must rely entirely on each other and the resources they have on board, a test of both technical skill and emotional fortitude. To bridge this gap, engineers are developing sophisticated artificial intelligence systems. These are not just databases, but true decision support companions that can analyze complex sensor data, run thousands of simulated outcomes in seconds, and present the crew with clear, prioritized options during an emergency. The crew's training, meanwhile, moves beyond rehearsing known scenarios. They must practice the art of extreme autonomy, learning to function as a self-sufficient, deep space civilization of a handful of people. This hazard forces a fundamental shift in how we conceive of exploration. It is no longer about sending instructions from Earth, but about sending capable, independent humans who can think, adapt, and survive when the comforting voice from home is just a memory echoing across millions of miles of void. In that vast silence, the ultimate test becomes not just technological but profoundly human. And if communication with Earth can fail, what happens when the intricate systems that keep the crew alive begin to whisper of their own impending failures? Every breath you take is a gift from a machine. In the sealed metal world of a spacecraft, there is no breeze, no open window, no fresh air drifting in from the outside. The entire atmosphere is a meticulously managed artifact, a closed-loop ballet of chemistry and biology that must run flawlessly for years. This is the life support system, and its failure is not a technical glitch. It is a direct countdown to catastrophe. Imagine the most complex, vital utility in your city: the water plant, the power grid, the sewage system, all compressed into a volume smaller than a shipping container and sent hurtling through a vacuum. A single cracked seal in an oxygen generator, a clogged filter in the carbon dioxide scrubbers, or a runaway bacterial bloom in the water recycler can trigger a cascade. The balance tips and the air grows thin or toxic. History offers a stark lesson in ingenuity under pressure. During the Apollo 13 mission, an explosion damaged the spacecraft, and the crew found themselves with rising levels of carbon dioxide. The square lithium hydroxide canisters from the command module were incompatible with the round openings in the Lunar module system. Using only materials on board, plastic bags, duct tape, a sock, and the cover of a flight manual, the crew and ground controllers engineered a makeshift adapter, famously known as the mailbox. This brilliant improvisation saved their lives, but it was a desperate fix for a short-term crisis. On a multi-year journey to Mars, there is no quick return, no ready backup module. The systems must be so reliable that they border on boring. This pushes engineers toward two parallel philosophies. The first is redundancy upon redundancy, designing every critical component with multiple, independent backups, and making the systems simple enough for the crew to repair with the tools and parts they carry. The second, more visionary approach looks to nature itself, biological life support. Instead of just machines scrubbing carbon dioxide, imagine compartments filled with algae or racks of carefully selected plants. These living systems could do more than just regenerate air and water. They could provide a psychological boost, a touch of green in the sterile gray, and even contribute to the crew's food supply. But integrating biology adds its own layer of complexity. Plants need light, they can get sick, and their life cycles must be perfectly synchronized with the crew's needs. The ultimate goal is to create a truly symbiotic habitat where human waste nourishes the plants, and the plants renew the air and water, a tiny, traveling piece of Earth's biosphere. This hazard forces a humbling perspective. On our planet, we take the background processes of life utterly for granted. The oxygen in the air, the water cycle, the microbial communities that break down waste, these are global, resilient, self-correcting systems that have operated for eons. In space, we must reinvent all of it from scratch inside a fragile shell, and we must get it perfect every single day. The margin for error is zero. A spacecraft's environment is not a home, it is a life raft, and every pump, every sensor, every leafy green shoot is a thread holding it together. When those threads are the only thing between a crew and the void, their reliability becomes the most profound engineering challenge of all. Even the most perfectly engineered life support system means nothing if the crew cannot bring themselves to eat. The dinner plate becomes a critical front in the battle for mission success. a complex equation of biology, psychology, and engineering. For a short mission, astronauts can rely on pre-packaged, freeze-dried meals, but for a journey lasting years, this simple solution unravels. The first enemy is time itself. Space radiation slowly degrades the vitamins and nutrients within stored food, so a meal that was perfectly balanced at launch could be nutritionally deficient by the time it is consumed months later. The second, more insidious foe is monotony. Imagine eating the same dozen meals with the same textures and flavors week after week, month after month. This leads to a well-documented phenomenon called menu fatigue, where astronauts simply lose their appetite. They undereat not out of necessity, but out of a deep psychological aversion. On the International Space Station, crews have sometimes lost dangerous amounts of body mass despite having plenty of food available, simply because they could not stomach another meal from the limited menu. This is more than a matter of comfort. It is a direct threat to health, weakening muscles, impairing immune function, and degrading cognitive performance. The solution lies in creating a living larder. The psychological lift from tending a plant and eating something fresh and crisp is immense, a tangible connection to growth and life in a sterile metal environment. Research into advanced hydroponic and aeroponic systems is in full swing, experimenting with growing leafy greens, vegetables, and even small fruits in transit. These are not simple window box gardens. They are high-tech life support modules where light, nutrients, and water are delivered with laboratory precision. Yet these systems introduce a new web of vulnerabilities. They are power-hungry. A prolonged loss of electricity means the death of the crop. They are biologically delicate. A single fungal spore or a bacterial blight could wipe out an entire harvest. A plant disease in the confined ecosystem of a spacecraft could spread with alarming speed. A failure in food production is a slow-motion emergency. It would not trigger alarms like a hull breach, but over weeks and months, it would erode the crew's physical resilience and mental sharpness, quietly undermining every other system designed to keep them safe. The challenge, therefore, is to move beyond seeing food as mere cargo and to view it as an integrated, living component of the habitat, one that nourishes both the body and the human spirit, and whose failure could unravel the mission from the inside out. This intimate reliance on cultivated life highlights another hidden danger, one where the very tools of survival can become instruments of harm. The most dangerous moments of any interplanetary mission are not spent in the void, but in the desperate rush to escape or embrace a world. This is the peril of the gravity well, a deep pit of physics from which a spacecraft must claw its way out or plunge safely into. Every planet holds its captive with an invisible hand, and breaking that grip, or surrendering to it without being shattered, demands a violent and perfect ballet of engineering. Consider the final approach to Mars. After months of serene coasting, the spacecraft must now slam into the thin Martian atmosphere at over 12,000 miles per hour. In minutes, it must transform from a celestial cruiser to a blazing meteor, then to a glider, and finally to a hovering lander. The heat shield, a blunt ceramic and carbon composite disc, becomes the only thing between the crew and plasma temperatures hot enough to vaporize steel. A single flaw in its construction, a chip from a micrometeoroid strike months earlier, could allow that superheated gas to burn through, dooming the vehicle in an instant. The atmosphere itself is the wild card, its density shifting with dust storms and seasons, requiring the onboard computer to make constant, split-second adjustments to the descent path. A parachute must deploy at hypersonic speeds, enduring forces that could rip ordinary fabric to shreds. Then, in the final moments, retro-rockets must fire with impeccable timing to arrest the last bit of velocity, settling the massive lander on uncertain, rocky ground. There is no runway, no control tower, and no second attempt. Every step is automated and irreversible. the terror of entry is matched only by the tension of ascent. To leave Mars, the crew must climb back out of that gravity well in a vehicle that has been sitting idle on the surface for perhaps a year or more. This ascent stage is their only ticket home, and it must light its engines perfectly the first time, in an environment where every valve and pump has been subjected to freezing nights, dust infiltration, and cosmic radiation. There is no launch pad crew to perform last-minute checks, no ability to scrub the launch for bad weather. An abort during ascent from Mars is a concept with few viable options, often meaning a forced return to a surface habitat that may no longer be intact. This condensed sequence of events, lasting perhaps only an hour from atmospheric interface to touchdown or from liftoff to orbit, represents the ultimate compression of risk. Years of mission planning, billions in resources, and human lives all converge on a handful of automated maneuvers where a single sensor glitch or a fraction of a % error in thrust can mean the difference between triumph and silence. It is a reminder that in space exploration, the journey is often the stable part, bookended by moments of controlled, breathtaking violence where the margin for error is measured in millimeters and milliseconds. The ship's brain is under constant, invisible assault. While a solar storm's radiation poses a direct threat to the crew, its charged particles wage a parallel war on the spacecraft itself, targeting the delicate electronic nervous system that keeps everything alive. This is the hazard of space weather versus technology, where the most critical failures may happen without a single shudder in the hull. The primary weapons in this conflict are tiny and devastating. High-energy protons and heavy ions from cosmic rays or solar flares can strike a computer chip like a microscopic bullet. When they hit the right spot, they can cause what engineers call a single event upset. This is not a physical burn, but a digital ghost, a single bit of memory flipping from a 0 to a 1, or vice versa, in an instant. The result can be an erroneous command, a corrupted data file, or an unexplained system reset. Imagine your home computer suddenly deciding to delete an important document or restart itself without warning. Now imagine that computer is controlling your air supply, your course to Mars, or the firing sequence of your landing engines. The potential for cascading error is profound. Beyond these sudden, random glitches lies a slower, more insidious decay. The same radiation that degrades human tissue also batters the spacecraft's components over years. Solar panels, the lifeblood of power generation, slowly lose efficiency as particles damage their crystalline structure. Cameras and scientific sensors can develop hot pixels or lose sensitivity, like a gradual blindness setting in. Wiring insulation can become brittle. This cumulative damage is a war of attrition, silently reducing the ship's capabilities mile by mile across the solar system. The nightmare scenario, however, is the sudden and total kill. An extreme solar particle event, a direct hit from the most energetic part of a coronal mass ejection, can deliver a massive surge of current through a spacecraft's electronics. This is not a bit flip but an electronic heart attack, a frying of critical circuits that leaves a component permanently disabled. In a worst-case event, this could mean the loss of primary computers, navigation systems, or communication arrays. The chilling outcome is a ship that is physically whole, with a crew alive and well inside, but rendered utterly brain-dead. A silent, drifting tomb unable to call for help or alter its course. Our defense is a discipline called radiation hardening. It involves both physical armor and digital intelligence. Physically, sensitive electronics can be housed in their own mini-fortresses, shielded with layers of tantalum or specially formulated plastics. But shielding is heavy, and every kilogram dedicated to protecting a computer is a kilogram not used for something else. The digital defense is perhaps more elegant, error-correcting software and hardware. These systems constantly check the spacecraft's memory for the telltale signs of bit flips, automatically finding and fixing the errors before they cause a problem. Critical systems are often triplicated, with 3 separate computers voting on every decision. If one is struck by a particle and gives a crazy answer, the other 2 outvote it and the mission continues. Yet no hardening is perfect. The trade-offs are constant between weight, power, cost, and risk. This hazard forces a sobering realization. In deep space, we are not just protecting flesh and blood. We are protecting the artificial intelligence and fragile silicon upon which that life absolutely depends. The ship is not merely a vessel, it is a patient, and space weather is a persistent, degenerative illness we must diagnose and counteract in real time, millions of miles from the nearest technician. A new community thrives within the sterile walls of the spacecraft, one we brought with us. Every human is a walking ecosystem, home to trillions of bacteria and fungi that live harmlessly on our skin and inside our bodies. In the sealed, recycled environment of a deep space habitat, this microscopic community is cut off from Earth's vast microbial network. It becomes an island, and evolution on islands takes strange turns. Everyday bacteria like Staphylococcus or common gut microbes can adapt to their new, simplified world. Studies suggest that in the unique conditions of microgravity, some bacteria can form thicker, more resilient biofilms, slimy protective layers that make them harder for antibiotics to penetrate. They might even exchange genetic material more readily, potentially sharing traits for antibiotic resistance. We are unintentionally cultivating a novel microbial environment right alongside the crew. At the very same time, the crew's primary defense against this community is being undermined. The combined stress of microgravity, radiation, and confinement triggers a state researchers term spaceflight-associated immune dysregulation. It is as if the body's security forces become confused and lethargic. Key immune cells like T cells and natural killer cells show reduced activity. The body's inflammatory responses can become dysregulated, sometimes overreacting to minor threats or failing to react adequately to real ones. Think of it as a fortress where the walls are slowly thinning while the guards inside are growing tired and inattentive. This combination is the perfect storm for infection. A routine illness like a urinary tract infection or a skin abscess caused by a now hardier bacterium could escalate in a body with a weakened ability to fight it. In the confined quarters with shared air and surfaces, such an infection could spread rapidly to the entire crew. The scenario mission medics dread is not a dramatic trauma, but a slow, debilitating outbreak of a resilient infection. With a limited pharmacy on board, the possibility of antibiotic resistance is a terrifying prospect. There is no hospital to transfer to, no specialist consultation, and certainly no emergency evacuation that could return a patient to Earth in time. A single persistent infection could consume medical resources, sap crew strength, and potentially force an abort if key personnel become too ill to perform critical duties. The defense, therefore, must be proactive and constant. It begins with relentless environmental monitoring, swabbing surfaces, and sampling the air to map the ship's microbiome, watching for dangerous shifts. Advanced multi-stage air filtration systems that can capture particles down to the viral level become essential utilities, not just comfort features. Perhaps most crucial is the need for a compact, AI-powered medical diagnostic lab, a device that could analyze a blood or saliva sample in minutes to identify a pathogen and its antibiotic resistance profile, allowing for precise, targeted treatment with the limited drugs on board. This hazard forces us to see the spacecraft not just as a machine, but as a fragile, interconnected biosphere. We are not merely transporting humans, we are transporting an entire microscopic world that evolves with us, and our survival depends on maintaining a precarious balance with the life we cannot even see. The body's internal clock is ticking to the wrong rhythm. In the perpetual twilight of a spacecraft or under the alien skies of another world, one of our most fundamental anchors vanishes, the reliable 24-hour cycle of day and night. Our circadian rhythm, the intricate biological clock governing sleep, hormone release, and cellular repair, evolved over eons to sync perfectly with Earth's rotation. Sever that connection, and the human system begins to drift into a state of profound internal confusion. On a journey to Mars, this is not a minor inconvenience. It is a slow burn hazard that erodes the very foundation of crew performance. The lighting inside a spacecraft is typically constant and artificial, lacking the dynamic color and intensity shifts of natural sunlight that tell our brains when to be alert and when to wind down. This can lead to chronic, low-grade sleep deprivation, where crew members might get enough hours of rest but never achieve truly restorative sleep. The consequences cascade. Metabolic processes become disordered, affecting how the body processes nutrients and stores energy. Cognitive function dulls, with impacts on memory, problem-solving, and attention to detail. Mood can become volatile, increasing irritability and social friction within the confined crew. Now consider arriving at Mars itself. A Martian day, called a sol, is about 24 hours and 37 minutes long. That extra 37 minutes might seem trivial, but to a human circadian rhythm finely tuned to a 24-hour cycle, it is a persistent daily mismatch. It is the equivalent of flying westward across 1.5 time zones every single day, a state of permanent, low-level jet lag that the body can never fully overcome. Imagine trying to maintain peak mental acuity and flawless teamwork while feeling perpetually out of sync, as if you are always slightly behind or ahead of where you need to be. The risks are operational as much as they are biological. A sleep-deprived engineer might misread a diagnostic report. A fatigued pilot might have a delayed reaction during a critical landing sequence. A commander with impaired judgment might make a poor call during an emergency. The margin for error in deep space is too thin to accommodate groggy minds. Countering this threat requires a science of artificial suns. Modern spacecraft and habitats are integrating advanced LED lighting systems that do far more than just illuminate. They are programmed to simulate a natural day, shifting from bright, blue-rich light in the morning to suppress melatonin and promote alertness, then gradually warming to amber and red tones in the evening to stimulate melatonin production and encourage sleepiness. This technological sunrise and sunset is paired with non-negotiable crew protocols, strict sleep schedules, designated dark and quiet hours, and even the use of specialized glasses to block sleep disrupting blue light before bed. The goal is to impose a healthy rhythm where nature no longer provides one. This hazard reveals a subtle truth about human spaceflight. We must engineer not only the air and water, but time itself. We must become architects of dawn and dusk, caretakers of the internal rhythms that make us human. Ignoring the tick of the biological clock is to risk unraveling the crew's cohesion and competence from the inside, one restless night at a time. The dream of sustainability on another world hinges on a single, dangerous gamble. For a crew to survive long-term on Mars or the Moon, they cannot possibly bring everything they need from Earth. The weight and cost would be astronomical. The solution is a concept called In-Situ resource utilization, the elegant idea of living off the alien land. It means turning Martian ice into drinking water, cracking the carbon dioxide atmosphere to create breathable oxygen, or processing lunar soil to extract building materials. On paper, it is the key to a permanent foothold beyond Earth. In reality, it is a chain of potential disasters waiting to happen. These are not simple machines. Imagine a robotic refinery operating autonomously for months before the crew even arrives, subjected to dust storms, cosmic radiation, and temperature swings that shatter metal. It must drill into unknown strata, heat frozen soil, and chemically process the results with perfect precision. A single clogged filter, a fractured drill bit, or a power fluctuation could halt the entire operation. If the water extraction plant on Mars fails, the crew's carefully calculated reserves from Earth become their only lifeline, and the clock starts ticking. If the system to make return fuel from the atmosphere malfunctions, the crew faces the unthinkable prospect of being stranded, with a perfectly good ascent vehicle sitting uselessly on the surface, empty. This transforms the very tool meant to ensure independence into a potential single point of catastrophic failure. The countermeasure is a painful trade-off. To be safe, you bring massive backup reserves from Earth, enough water, oxygen, and fuel to complete the entire mission without any local resources. But launching all that mass from our deep gravity well is perhaps the single greatest cost in space exploration. It could make the mission financially impossible. So we are caught in a fundamental tension between the bold, efficient vision of true interplanetary settlement and the conservative, risk-averse demands of human safety. Do we bet the lives of a crew on machinery that has never been tested at this scale, in this environment, for this long? Or do we burden the mission with such immense cost that it never flies at all? The path forward likely lies in painful, incremental steps. Robotic precursor missions must not only test the technology, but torture it, pushing it to failure so we understand its limits. The first human crews will arrive with enough supplies to survive without the local factory, treating its output as a bonus, not a requirement. Only after years of demonstrated, reliable operation does the in-situ plant become the trusted cornerstone it was meant to be. This hazard teaches a sobering lesson about our expansion. We cannot simply transplant Earth's industrial processes to another world. We must invent an entirely new discipline of extreme environment robotics and chemistry, where every successful extraction of a liter of water or a gram of oxygen is a hard-won victory against a profoundly indifferent landscape. Every biological system produces waste, and in the artificial biosphere of a spacecraft, there is no away. The 15th hazard is the unending, unglamorous cycle of consumption and expulsion, where a single clogged filter can trigger a cascade of toxic consequences. Human waste is not merely a matter of sanitation. It is a complex chemical and biological payload that must be actively managed. Left to accumulate, it decomposes, releasing ammonia and other compounds that can poison the recycled atmosphere. A malfunctioning toilet or a leak in the waste storage system does not just create a mess. It introduces a direct biological hazard into the crew's living space, risking infection and creating an environmental crisis within the sealed walls. The challenge is to transform this problem into a resource. Advanced systems aim to recycle every drop of water from urine and sweat, and even process solid waste into inert material or, in future concepts, into nutrients for plant-based life support. But these processors are intricate chemical factories, vulnerable to scaling, bacterial blooms, and mechanical failure. Their constant, reliable operation is as critical as the oxygen generators, for in a closed loop, a toxin introduced anywhere eventually circulates everywhere. This internal challenge is mirrored by an external one of profound responsibility: planetary protection. The spacecraft carries with it a microscopic cloud of Earth life, bacteria and spores clinging to every surface and sealed within every component. This creates the risk of forward contamination, accidentally seeding another world with our microbes. If we were to discover potential signs of life on Mars, how could we be certain they were not simply hitchhikers from our own labs? A single Earth bacterium deposited in a Martian brine pocket could ruin forever our chance to answer the universe's most profound question: are we alone? To prevent this, spacecraft destined for sensitive areas like the Martian polar caps or the subsurface ocean moons of Jupiter and Saturn are assembled in sterile clean rooms and sometimes baked in ovens to exterminate any stowaways. It is a meticulous, costly process of biological quarantine. The reverse scenario, back contamination, presents a different kind of planetary defense. If a sample return mission brings Martian rocks or soil back to Earth, what if that material contains a dormant, unknown microorganism? The risk of an extraterrestrial pathogen to Earth's biosphere is considered extremely low by scientists, as any Martian life would have evolved along a completely separate tree for billions of years, unlikely to interact with our biology. Yet the consequence of being wrong is so vast that the principle of extreme caution governs all planning. Any returning sample would be treated as potentially hazardous until proven otherwise, contained within multiple layers of secure, fail-sealed facilities, and studied with robotic handlers before any human is ever exposed. This dual mandate, to keep other worlds pristine for science, and to keep our own world safe from the unknown, adds a layer of immense ethical and technical complexity to every mission plan. It means our journey outward is not a reckless expansion, but a careful, deliberate extension of our stewardship, where even our waste and our microscopic passengers must be accounted for in the grand equation of survival. A spacecraft is a single, interconnected nervous system. The 16th hazard emerges from this very integration, where every breath of air, every watt of power, and every course correction is woven into a seamless digital tapestry. This deep interdependence, the hallmark of modern engineering efficiency, creates a hidden vulnerability, the catastrophic cascade. A single fault is no longer an isolated problem. It is a spark that can race through the ship's entire architecture. Consider a routine power fluctuation from a damaged solar panel. Instead of just dimming the lights, that surge might trip a safety relay in the primary life support computer. As the system reboots, the carbon dioxide scrubbers cycle offline for just a few critical minutes. Carbon dioxide levels begin to climb, triggering environmental alarms. The crew, now distracted by the air quality alert, might miss the initial diagnostic message about the power regulator. To stabilize the atmosphere, they command a reboot of the main environmental control, which draws a sudden, high load from the already stressed electrical system, causing a second, larger surge that finally fries the navigation system's primary processor. What began as a glitch in a solar array has now degraded air quality, scrambled diagnostics, and blinded the ship's sense of direction, all within a chaotic half-hour. This is the nightmare of interdependence, where systems are so tightly coupled that a failure in one can propagate in unpredictable, nonlinear ways, creating a crisis far greater than the sum of its parts. The solution lies in a philosophical shift from mere redundancy to deliberate isolation. Engineers call it graceful degradation or fault containment. The goal is to design the vessel so that when a component fails, its failure is contained like a firebreak in a forest. Non-critical systems can be sacrificed to preserve the core triumvirate of survival: breathable air, potable water, and basic power. This might mean designing separate, independent power buses for life support and propulsion, so a surge in one cannot jump to the other. It requires software that can automatically isolate malfunctioning modules and reroute functions, all while providing the crew with a clear, simplified picture of what is still working, not just what is broken. It is the art of designing a ship that can become simpler, more robust, and more focused on pure survival as it is wounded, rather than a complex machine that spirals into total paralysis. This hazard forces a counterintuitive lesson upon us. In the depth of space, the most advanced system may not be the one with the most connections, but the one with the smartest disconnections. Our survival may depend not on building a perfect, unbreakable hull, but on crafting a vessel that knows how to break apart in the right way, preserving the fragile flame of life inside as everything else goes dark. The human body is a map of Earth drawn by gravity and time. We have studied its adaptations in low Earth orbit for months, but a journey to Mars is a voyage into uncharted biological territory. The 17th hazard is the vast landscape of unknowns in long-duration spaceflight biology. What happens to a human system after 2, even 3 years, completely untethered from our planet's influence? The data from the International Space Station is invaluable, but it is a safe harbor compared to the open ocean of interplanetary space. There, beyond the protective embrace of Earth's magnetic field, the cumulative radiation dose is higher and the isolation more absolute. Could this prolonged exposure trigger subtle, unforeseen neurological changes that only manifest years later, affecting cognition or mood in ways we cannot yet predict? Might the constant fluid shift toward the head over such an extended period cause irreversible alterations to the structure of the eyes or the integrity of the vascular system? Changes that do not simply reverse upon return to gravity. We must also consider the stability of the complex microbial world within each astronaut. Could the unique stresses of deep space disrupt this delicate balance in permanent ways, or reactivate latent viruses that the body usually keeps in check? These are not just known problems we can engineer against. They are the unknown unknowns, questions that only the first mission to Mars itself can truly answer. This transforms those pioneering crews into something more than explorers. They become the final, essential test subjects in the grandest biomedical study ever conceived. Such profound uncertainty demands a framework of extreme precaution. It necessitates continuous, sophisticated biomedical monitoring throughout the mission and for decades after, turning each astronaut's life into a longitudinal study for the benefit of all who follow. It may also require new ethical frameworks for informed consent, where explorers fully understand they are stepping into a biological frontier, accepting risks that medicine cannot yet fully name or measure. This hazard is a humbling reminder that no amount of simulation can replace the reality of the journey, and that the ultimate discovery on Mars might be a new understanding of ourselves. Precision is a currency spent with every passing kilometer. The 18th hazard is a silent mathematical specter, the unforgiving physics of navigation and orbital mechanics. This is not like steering a ship on an ocean where a slight turn of the wheel brings a gradual change in course. In the void, you are a stone thrown across a canyon of invisible forces, and the aim must be perfect from the very beginning. The spacecraft's trajectory is a calculated dance with gravity, a path plotted years in advance that threads the needle between the gravitational pulls of the Sun, Earth, and the target planet. A tiny error in a course correction burn, a thruster firing for a fraction of a second too long or pointed a hair's breadth off axis, doesn't just nudge you off course. It magnifies over millions of miles. A velocity error as small as 1 centimeter per second at the midpoint of a journey to Mars could translate into missing the planet entirely by hundreds of kilometers, a fatal overshoot into the endless dark. Fuel is the most precious and non-renewable resource on board, and every kilogram used to correct a navigation mistake is a kilogram not available for the crucial maneuvers of orbit insertion or the return home. This turns every minor adjustment into a high-stakes gamble. Knowing your exact position in the featureless black is its own monumental challenge. The spacecraft must constantly triangulate its location using the ancient guideposts of pulsars and stars, internal gyroscopes that track every minute rotation, and radio signals from Earth that grow fainter and more delayed with distance. A solar storm can scramble those radio signals with static. A critical star tracker, its lens clouded by a speck of dust or damaged by radiation, can leave the ship momentarily blind. In that fragile moment of uncertainty, the vessel is essentially guessing its way through the solar system. The complexity spikes dramatically when approaching small, irregular worlds. Navigating near an asteroid or one of Mars's lumpy moons like Phobos or Deimos is like trying to orbit a potato. Their gravity fields are not smooth and symmetrical like a planet's, but lumpy and unpredictable, tugged by hidden mass concentrations beneath their surfaces. A spacecraft relying on standard orbital equations could find itself unexpectedly pulled off course, requiring constant fuel-guzzling thruster firings just to maintain a stable path. This is celestial billiards at a cosmic scale, where the cue ball is a billion-dollar ship carrying human lives, and the table is shaped by forces we can only partially map. Success depends on a flawless conversation between human intuition back on Earth and the cold, perfect logic of the onboard computer, a partnership that must hold firm across the ever-widening gulf of light seconds. One misunderstood decimal point, one missed software update, and the story ends not with a landing, but with a quiet, eternal drift. Beyond our solar system's familiar dangers lies a violence of truly cosmic proportions. The 19th hazard is not a local storm, but a flash from the edge of the observable universe, a gamma-ray burst. These are the most powerful explosions known to exist, born from the catastrophic collapse of massive stars or the merger of ultra-dense neutron stars. In a few seconds, such an event can release more energy than our Sun will emit in its entire 10 billion-year lifetime. That unimaginable power is focused into twin, narrow beams of pure gamma radiation, lances of light that scream across the galaxy. For a spacecraft or a planet unfortunate enough to be in the direct path of that beam, the consequences are instantaneous and absolute. The torrent of high-energy photons would not just pass through a ship's hull, it would overwhelm it. In mere moments, it could deliver a radiation dose thousands of times greater than a lethal amount, a flash so intense that current shielding concepts offer no meaningful defense. The event would be over before any alarm could sound. The secondary effects are just as chilling. If such a beam struck a planet like Mars, even from a great distance, the radiation could chemically shred the atmosphere, destroying any protective ozone layer and bathing the surface in ultraviolet light for years afterward, sterilizing a world that might have harbored life. This transforms the hazard into a statistical ghost. The probability of a spacecraft on a Mars mission intersecting the narrow beam of a nearby gamma-ray burst is vanishingly small, perhaps a 1 in a million chance per century. But it is not zero. That tiny, non-zero probability introduces a profound philosophical tension into mission planning. How do you prepare for an event that is both astronomically unlikely and astronomically lethal? You cannot armor against it, you cannot outrun it, you can only acknowledge it as part of the cosmic background risk, the ultimate reminder that we are not just navigating a solar system, but a galaxy capable of sudden, unimaginable fury. This hazard represents the final layer of the cosmic lottery, where the grand prize is a silent, instantaneous end against which our most brilliant engineering is, for now, simply irrelevant. It forces a humbling perspective. Our survival among the stars depends not only on solving the problems we can see, but on enduring the random violence of a universe that does not know we are here. A mission can have perfect hardware and still fail because of a single, simmering argument. The 20th hazard is the slow erosion of trust and cooperation within the crew itself, a social dynamic failure that can unravel years of preparation in a matter of weeks. We can select the most psychologically resilient individuals, but the pressure cooker of a multi-year mission, with its isolation and immense stress, creates a unique social crucible. Conflicts over perceived unequal workloads, fundamental personality clashes, or simmering resentment over decisions made by mission control millions of miles away have no external outlet. There is no walking away, no weekend off, no new faces to provide perspective. In the confined, recycled air of the habitat, a minor grievance can fester and magnify, evolving into a communication breakdown that paralyzes the team. This is not speculation. Research from analogous environments like Antarctic winter overstations and long-duration submarine patrols provides a clear map of the danger. Groups can fracture into cliques, collaboration turns to silent compliance or outright refusal, and the shared mission goal is lost in a fog of interpersonal tension. A crew in this state is a profound liability. In an emergency, split-second cooperation is essential. A team that cannot communicate openly, that harbors distrust or refuses to follow a commander's lead, cannot possibly execute the complex, synchronized procedures needed to survive a crisis. The technology becomes irrelevant if the humans operating it are no longer a unified whole. Mitigation begins long before launch, with crews undergoing extensive, immersive team training in environments that simulate the stress and isolation of spaceflight. They are not just taught conflict resolution, they are forced to practice it under pressure, building a shared language for addressing friction before it becomes toxic. The design of the habitat itself becomes a tool for social health. Contrary to the cramped quarters of early spacecraft, future interplanetary vessels must include private, personal spaces, small sanctuaries where an individual can retreat, be alone with their thoughts, and regain emotional balance. The constant, open-plan existence of early concepts is a recipe for social overload. This hazard forces a fundamental shift in perspective. The social architecture of the mission, the unspoken rules, the shared culture, the bonds of trust, is not a soft, secondary concern. It is as critical a system as the oxygen generators or the navigation computer, and it requires the same level of careful, intentional engineering and continuous maintenance. A spacecraft is a machine, but the crew within it is a living, breathing society, and its cohesion is the most fragile and essential component of all. Even a simple toothache becomes a life or death equation millions of miles from home. The 21st hazard strips away the comforting infrastructure of civilization, leaving a crew to face a medical crisis with only the tools and knowledge they carry. What happens when an astronaut develops acute appendicitis, suffers a severe burn during a repair, or shows signs of a cardiac event? On Earth, these are serious but manageable situations, met with ambulances, emergency rooms, and teams of specialists. In transit to Mars, the nearest hospital is over a year away, and evacuation is a physical impossibility. This forces a brutal new discipline, autonomous deep space medicine. The crew's medical officer is not just a doctor, but a surgeon, pharmacist, psychiatrist, and dentist, all rolled into one. Their training must be extraordinary, covering trauma, emergency surgery, and diagnostic procedures they would never perform alone on Earth. They must be prepared to operate on a colleague in microgravity, where blood does not pool but forms floating spheres, and where every instrument must be tethered or it becomes a lost projectile. The medical suite itself is a masterpiece of miniaturization, containing a compact ultrasound machine that doubles as an imaging tool for broken bones and internal injuries, a dental drill, a small pharmacy, and perhaps even a robotic surgical assistant. Yet its capabilities are defined by stark limits. It cannot carry an MRI machine or a full blood bank. Every gram of medication, every suture, every dose of anesthetic is accounted for with painful precision. The challenge is deepened by space physiology itself. Medications behave differently in the human body under microgravity and radiation stress. A standard antibiotic dose might be less effective, or a painkiller might metabolize too quickly, leaving a patient in agony. The medical kit cannot be a simple copy of an Earth hospital's inventory. It must be custom designed for the altered human body in flight. communication delays render real-time telemedicine useless in an emergency. By the time a video of a patient's symptoms reaches Earth and a specialist's advice returns, the critical window for intervention may have closed. The crew must therefore train for scenarios where they are the final authority, making irreversible decisions with imperfect information. This hazard confronts a profound psychological burden. It is one thing to risk your own life, it is another to hold the life of a friend in your hands, knowing that a mistake in procedure or a misdiagnosis could cost everything. It transforms the mission into a pact of ultimate trust, where survival depends not just on technology, but on the depth of a crewmate's skill and calm under the most extreme duress imaginable. The medical log becomes one of the most critical documents on board, a record of how humanity learned to heal itself when there was truly no one else to call. The spacecraft's skin is under a slow, invisible siege. The 20-second hazard is the relentless degradation of materials in space, an environment that acts as a cosmic torture chamber for every bolt, wire, and panel we send into the void. This is not a sudden, dramatic failure, but a patient, grinding assault that works its damage molecule by molecule over years. In the tenuous upper atmosphere of low Earth orbit, a particularly insidious agent waits. Atomic oxygen, a highly reactive form of the element, doesn't exist naturally on our planet's surface, but it's abundant where satellites fly. As a spacecraft orbits at tremendous speed, these individual atoms slam into its surfaces with enough energy to literally scrub away protective coatings, eroding solar panel blankets and dulling reflective surfaces like sandpaper over time. Meanwhile, unfiltered ultraviolet radiation from the sun bombards everything. For many plastics and polymers, this constant barrage breaks the long chains of molecules that give them strength and flexibility. What was once a supple wire insulation or a resilient seal gradually becomes brittle and weak, prone to cracking under the slightest stress. Windows and camera lenses can darken or develop a permanent haze, slowly blinding the vessel's critical eyes. The assault intensifies in deep space, governed by a brutal thermal rhythm. In full sunlight, a surface can soar to temperatures hot enough to boil water. Minutes later, as the craft rotates or moves into shadow, that same surface plummets to hundreds of degrees below freezing. This extreme thermal cycling happens not over seasons but over hours. Metals, composites, and glass expand with heat and contract with cold, and this repeated flexing over thousands upon thousands of cycles induces material fatigue. Microscopic cracks form, propagate, and join together, silently compromising the integrity of a load-bearing strut or the seal of a pressurized module. This process is compounded by the constant peppering of micrometeoroids, which leave behind microscopic pits and craters. Each pit is a stress concentrator, a tiny fault line where a larger crack can begin. The combined effect is a spacecraft that ages in dog years, its youthful resilience steadily worn down by the unceasing elements. A wire that seemed perfectly protected at launch might have its insulation turned to a fragile shell after 2 years near Mars. A critical structural bracket, subjected to endless expansion and contraction, could develop a hairline fracture invisible to the naked eye. This slow-motion decay forces a radical shift in engineering philosophy. We cannot simply use the best materials from Earth. We must invent entirely new ones specifically forged for the cosmos. Laboratories are developing self-healing polymers that can automatically seal small cracks, ultra-white coatings that reflect heat and resist darkening, and nanocomposites designed to withstand atomic oxygen erosion. But even the most advanced material has a limit. Therefore, the second line of defense is vigilant, robotic eyes. Future interplanetary ships will need comprehensive in-flight inspection systems, likely swarms of small internal and external cameras or crawling robots equipped with sensors. Their mission will be to constantly scan the hull, joints, and critical components, using algorithms to compare today's image with one from yesterday, searching for the first telltale sign of a new crack, a discolored patch, or an area of unexpected wear. The goal is to catch degradation not at the moment of failure, but in its earliest, most manageable stage, allowing for a planned repair or a rerouting of systems long before a tiny crack becomes a catastrophic breach. This hazard teaches us that in space, nothing stays new. Our technology must be designed not for a pristine launch day, but for a long, hard life of weathering a storm that never, ever lets up. A deep psychological trap is built into the very machinery of survival. When every fundamental need is met by a silent, incomprehensible black box, the human spirit can begin to atrophy. An astronaut might know which button to press to recycle water, but if the complex chemical processes inside remain a mystery, a subtle shift occurs. They transition from an explorer to a caretaker, from an active participant to a passive beneficiary of a technology they do not truly command. This dependence on systems whose failure means certain passing can breed a background hum of anxiety, a quiet sense of living on borrowed time inside a bubble they did not blow and cannot fully mend. The habitat, for all its life-giving function, risks becoming a gilded cage where the crew feels more like fragile cargo than capable pioneers. The antidote to this creeping helplessness is not more automation, but strategically less. It is the deliberate design of agency. Consider the profound psychological difference between watching a sensor confirm the air is clean and personally assembling and testing a new carbon dioxide scrubber cartridge with your own hands. One is monitoring, the other is mastery. The most resilient environments will be those that provide meaningful work tasks that are not busy work, but that have a direct, tangible, and understandable impact on survival and well-being. Successfully growing a lettuce plant from seed to harvest in a hydroponic bay does more than supplement the diet. It is a visceral reconnection to the cycle of life, a small act of creation and nurturing in a sterile metal world. It returns a measure of control. Repairing a malfunctioning exercise machine with fabricated parts does more than restore a piece of equipment. It reinforces competence and self-reliance, proving that the crew are not just inhabitants of their ship, but its stewards and mechanics. Mission architects now understand that the interface between human and machine must be designed for understanding, not just operation. Systems should be transparent and modular, built so the crew can trace the flow of air, follow the path of water recycling, and comprehend the principles at work. Training must go beyond emergency procedures to include the underlying why, empowering astronauts to improvise solutions with the tools at hand. This hazard reveals a fundamental truth about our nature. We are not built for perpetual passivity. Our mental health is intertwined with our sense of efficacy. To endure the years-long isolation of a Mars mission, the crew must feel like capable, integral parts of their own life support system, actively weaving the threads of their survival, rather than simply clinging to a tapestry woven by engineers long ago and far away. Their greatest strength may not be the technology that surrounds them, but the unshakable belief that they can understand it, fix it, and even improve it. Who holds authority when the only witnesses are the stars? The 24th hazard is a frontier of human conflict, the ethical and legal void of deep space. Our treaties and laws are woven from the fabric of life on Earth, bound by borders, jurisdictions, and shared cultural understandings. Beyond our planet, that fabric frays into ambiguity. The foundational Outer Space Treaty declares that space is the province of all humankind, forbids national claims of sovereignty, and mandates that states are responsible for their national activities. But this elegant framework was written for an era of robotic probes and flags planted by visitors, not for permanent human communities. Its silence on the gritty details of daily life off-world creates a profound gray zone. Imagine a tragic accident during the construction of a Martian habitat. If an astronaut from one nation is injured due to equipment manufactured in another, launched by an international consortium, who is liable? Which nation's courts hear the case? The complex web of earthly law becomes nearly impossible to untangle across 50 million miles of vacuum. More somber still are the protocols for the unthinkable. The loss of a crew member during a multi-year mission presents questions with no easy answers. How is the individual honored? What are the procedures for the care of their remains, balancing dignity with the harsh biological realities of a closed environment? Mission plans must include these difficult contingencies, creating guidelines that are both medically sound and deeply respectful, all without established precedent to follow. These questions extend to the living as well. A serious conflict erupts between two crew members, or between the crew and mission control over a critical decision. In the tense isolation, with Earth's authority delayed by 40 minutes of light travel time, who has the final say? Is the commander's authority absolute, or can a crew collectively override an order from the ground that they believe jeopardizes their safety? Without clear jurisdictional authority, a dispute could paralyze a mission, creating dangerous stalemates when decisive action is needed most. Even the dream of utilizing local resources is fraught with legal tension. The Outer Space Treaty prohibits national appropriation, but says nothing about a private company or an international collective mining water ice on the Moon. How are these resources allocated to prevent a cosmic gold rush that could lead to conflict? The hazard here is societal, not physical. It is the risk that a tragedy or a dispute becomes mired in unresolved legal questions, complicating emergency response and setting problematic, conflicting precedents for the nascent spacefaring civilization we hope to build. Solving this requires a new kind of diplomacy, one that happens not in the moment of crisis, but in the quiet rooms on Earth long before launch. We must craft new agreements, detailed codes of conduct, intercrew conflict resolution frameworks, and transparent protocols for resource use that all launching nations and entities agree to uphold. It is the unglamorous work of building the invisible infrastructure of trust and order, ensuring that when we finally establish a foothold on another world, we bring with us not just our technology, but a durable foundation for justice and cooperation. The ultimate test may be whether we can govern ourselves as wisely as we navigate the stars. The final frontier does not present its dangers one at a time. After mapping 24 distinct cosmic hazards, we arrive at the 25th, and perhaps most daunting of all. It is the ultimate hazard, the threat of synergistic risk. The universe's greatest danger may not be any single failure, but the terrifying potential for multiple crises to ignite at once, combining in unforeseen and catastrophic ways. Imagine a powerful solar storm that damages key electronics and communication arrays. In that moment of technological confusion, a crew member suffers a medical emergency requiring immediate, precise care. The team is now split, their attention fractured between diagnosing a ship-wide systems failure and performing a complex medical procedure, all while cut off from Earth's guidance. Each problem alone is challenging, but together they strain the crew's capacity to the absolute limit. This is the nightmare of concurrent contingencies. A micrometeoroid strike that silently compromises hull integrity could coincide with a cascading fault in the life support system software. The crew would be racing to patch a physical hole in their world, while also troubleshooting the very machines that keep the air inside it breathable. On a psychological level, the prolonged stress and isolation that erode group cohesion could also suppress immune function, creating the perfect conditions for a novel bacterial strain to take hold and spread rapidly through the habitat. In a synergistic emergency, 1 plus 1 does not equal 2, it equals a cascading 10. The whole becomes vastly more dangerous than the sum of its isolated parts. This concept forces a fundamental evolution in how we prepare. Mission architecture can no longer be about mitigating individual risks on a checklist. It must be about designing for holistic resilience, creating systems and training crews specifically for chaotic, compound failures. Engineers must move beyond simple redundancy. They need to design systems that are not only robust, but also fault-tolerant in a deeply interconnected way, so that the failure of one subsystem does not catastrophically disable 3 others. Crew training must escalate from rehearsing specific procedures to practicing the art of triage under overwhelming pressure. Simulations will deliberately layer multiple, unrelated emergencies, forcing teams to prioritize, adapt, and make heartbreaking decisions about where to allocate their limited attention and resources. The goal is to build a kind of operational antifragility, where a crew and their vessel can not only withstand shocks, but can reorganize and respond effectively when the entire rulebook is being rewritten in real time. This final hazard is a humbling acknowledgement of the universe's complexity. We can prepare for the dangers we can name, but deep space reserves the right to present them in combinations we have not yet imagined. The ultimate test of an interplanetary mission, therefore, may not be surviving any one cosmic hazard, but enduring the moment when several decide to arrive at the same time, demanding from a small group of humans a response of unimaginable calm, creativity, and courage. This daunting landscape reveals a single, powerful truth. The path to the stars is not cleared by eliminating every danger, but by building a civilization resilient enough to walk among them. Our future depends on a philosophy of layered defense, where no single point of failure can spell the end. This mitigation is not a single breakthrough, but a symphony of disciplines advancing in concert. Material science is forging the armor. We are moving beyond aluminum and steel to metamaterials that can absorb impacts and self-heal, to ultra-reflective coatings that defy radiation darkening, and to nanocomposites that laugh in the face of atomic oxygen. The hull of a Mars ship will be a living, responsive skin, monitored by swarms of microsensors, capable of diagnosing its own stresses and initiating repairs. Inside that fortress, we must rebuild a piece of Earth. Closed-loop biospheres transform the spacecraft from a sterile machine into a symbiotic organism. Algae chambers and hydroponic gardens do more than recycle air and water. They become psychological anchors, pockets of green life that nourish the spirit as surely as the body. They turn waste into nutrients and carbon dioxide into fresh food, creating a tiny, resilient echo of our planet's own cycles. To combat the body's slow unraveling, we must bring gravity with us. The elegant concept of rotational artificial gravity, a habitat module spinning to create centrifugal force, moves from science fiction to engineering blueprint. A slowly turning spacecraft could provide the gentle, constant pull needed to keep bones strong and fluids balanced, turning a years-long voyage from a physiological ordeal into a sustainable journey. The crew's silent partners will be intelligences of another kind. Advanced artificial intelligence will act as a co-pilot and a guardian, constantly analyzing millions of data points from ship systems and crew biometrics. It will predict failures before they happen, suggest optimal courses during a navigation crisis, and guide a medical officer through a complex procedure with real-time, adaptive instructions when Earth's advice is 40 minutes away. None of this can be done alone. The scale of the challenge demands a pooling of human genius across all borders. International collaboration is not just politically wise, it is technically essential. It combines resources, diversifies perspectives, and creates a shared framework of safety and ethics for this new frontier. Before any ship departs for Mars, its protocols are tested in the most extreme corners of our own world. Analog missions in the Arctic, in underwater habitats, and in vast, barren deserts like the Atacama serve as cosmic dress rehearsals. Here, crews test hardware, practice emergency scenarios, and learn the subtle art of living in profound isolation, refining the human element of the equation. The journey forward, therefore, is one of relentless, incremental preparation. It is a grand project of turning cosmic threats into manageable engineering challenges through knowledge, redundancy, and ingenuity. We meet each hazard not with fear, but with focused curiosity, systematically solving one puzzle after another until the once impossible journey becomes simply the next mission. Our journey through these 25 cosmic hazards reveals a sobering truth. Interplanetary travel is not a simple extension of a road trip. It is an act of supreme audacity. It demands we confront a universe that is, by its very nature, indifferent to the fragile bubble of biology we represent. Every one of these threats, from the silent rewriting of our DNA to the profound loneliness of the void, underscores a single fact. We are visitors in a realm that was not made for us, and yet here we are, meticulously mapping each danger, not as a surrender but as a declaration. This is the testament to human courage and ingenuity. We stare into that indifference and respond not with fear, but with focused curiosity, engineering, and an unshakable drive to push the boundaries of where life can go. By identifying and working to mitigate these hazards, we are doing more than plotting a course to Mars. We are charting a path toward a more resilient future for all of humanity. The solutions we forge for deep space, the closed-loop ecosystems, the radiation-hardened materials, the protocols for extreme autonomy will echo back to Earth, helping us build more sustainable communities and prepare for long-term challenges on our own planet. The stars do not make it easy, but that is precisely what makes the endeavor worthy. The difficulty is the point. It forces us to become better engineers, more cooperative societies, and more thoughtful stewards of life. As we conclude this exploration, consider this final reflection. Mastering this intricate web of cosmic hazards is the price of admission. It is the rigorous examination we must pass to earn our place as a spacefaring civilization, to move from being creatures of Earth to citizens of a wider cosmos. The voyage is daunting, but the destination is a transformed understanding of our own potential. If you found this deep dive into the frontiers of our future compelling, subscribe for more journeys into the technology and ideas that will take us there. We would love to hear your perspective. Share your thoughts in the comments below on which of these 25 hazards you find most formidable or most fascinating as we collectively look toward the stars.